Scientists just admitted they've been wrong about Jupiter for 50 years. Every textbook, every measurement, wrong. The largest planet in our solar system isn't the size we thought it was. NASA's Juno spacecraft found something impossible. Jupiter is smaller. Miles vanished from its equator. Entire regions flattened at the poles. We've been staring at this giant through telescopes for centuries, sent 4 spacecraft past it, put an orbiter around it, and somehow missed this. If you want to see how a planet the size of 1,000 Earths can hide the truth in plain sight, hit subscribe, because what we discovered changes everything we thought we knew about planets. Picture every astronomy class you've ever sat through, every documentary about the solar system, every textbook diagram showing Jupiter as this massive sphere dwarfing Earth. All of them share the same measurements: 88,846 miles across at the equator, 83,082 miles from pole to pole. These numbers have been gospel since the Voyager and Pioneer missions flew past Jupiter in the 1970s. They're wrong. The error is small. The error is real. And it's significant enough that scientists at the Weizmann Institute in Israel just published a paper in Nature Astronomy that's forcing a global rewrite. Jupiter is approximately 5 miles narrower at its equator than textbooks claim. At the poles, it's about 15 miles flatter. These are real measurements using technology that didn't exist when we took those first readings decades ago. Here's what makes this unsettling. We're talking about Jupiter, our neighbor, the planet we've studied longer and harder than any other gas giant in the universe. We have spacecraft orbiting it right now. We can literally watch its storms in real time with amateur telescopes from our backyards. And somehow, for half a century, we've been measuring it wrong. The researcher who led the study, Eli Galanti, put it bluntly: textbooks will need to be updated. That's scientist speak for admitting a fundamental error that ripples through everything we thought we knew, because Jupiter serves as the reference standard, the template, the blueprint we use to understand every gas giant we discover around other stars. If our measurements of Jupiter were off, then our measurements of hundreds of exoplanets might be off too. The problem traces back to how we measure planets that don't have a solid surface. Jupiter is a ball of gas and liquid with no ground to stand on. So where do you measure from? Scientists picked an arbitrary pressure level, 1 bar, the same pressure you feel standing at sea level on Earth, and called that the surface. Everything else is measured from there. Reaching that invisible line with precision requires more than just pointing a telescope and estimating. It requires a spacecraft to pass directly behind the planet as seen from Earth. When that happens, the radio signals beaming back to us bend through Jupiter's atmosphere. The amount of bending tells us exactly where that 1 bar pressure level sits. The Voyager and Pioneer missions only did this 6 times total. 6 data points to define a planet larger than 1,000 Earths. 6 measurements that became locked into scientific literature for 5 decades. Juno has now added 26 more measurements, and they tell a different story. The real question goes beyond why the measurements changed. What did we miss by getting them wrong in the first place? What else are we measuring incorrectly right now? Imagine trying to measure something you can never touch. Something with no edges, no boundaries, just layers of gas getting denser the deeper you go. That's the challenge with Jupiter. You can't drop a ruler on it. You can't walk around its circumference with a measuring tape. All you have are radio waves and mathematics. NASA's Juno spacecraft uses a technique called radio occultation. The name sounds complicated. The concept is beautifully simple. Juno orbits Jupiter in a long elliptical path. Sometimes that path takes it directly behind the planet from Earth's perspective. When that happens, Juno's radio signal has to punch through Jupiter's atmosphere to reach us, and atmospheres bend radio waves. Think of it like looking at a straw in a glass of water. The straw appears to bend at the surface because light travels at different speeds through air versus water. Radio waves do the same thing, passing through layers of atmosphere with different densities. The denser the atmosphere, the more the signal bends. By measuring exactly how much the signal curves, scientists can calculate the density at different depths. Maria Smirnova, a doctoral student who developed the processing technique, described it clearly. The radio beam goes through the atmosphere and bends a little bit. We measure that bending. The more it bends, the denser the atmosphere is at that point. Since we know exactly where Jupiter is, where Earth is, and where Juno is, we can determine the density at a specific distance from the planet's center. That lets us set up the radius and shape. Here's where it gets tricky. Jupiter doesn't just sit there peacefully while we measure it. The planet screams. Storms rage across its surface at hundreds of miles per hour. These are jet streams that could shred any aircraft we've ever built. And those winds create their own forces that push and pull on the atmosphere, changing its shape in ways that earlier measurements completely ignored. The original Voyager and Pioneer measurements treated Jupiter like it was static, like a basketball just sitting there spinning. They didn't account for the fact that those massive atmospheric bands, the stripes you can see through a backyard telescope, are violent rivers of wind creating their own centrifugal forces. Forces that bulge the atmosphere outward in some places and squeeze it inward in others. Juno's extended mission, which started in 2021, put the spacecraft on a new trajectory that changed everything. Previously, Juno never passed behind Jupiter from our viewpoint on Earth. The original orbit didn't allow it. The mission extension adjusted that path, and suddenly scientists had opportunities they never had before. Opportunities to watch radio signals bend through different parts of the atmosphere, to map temperatures and pressures in unprecedented detail. 26 measurements, where there used to be 6, and with each measurement, the picture of Jupiter shifted. What emerged was a planet far more dynamic and complex than anyone had imagined. A world that's been hiding its true nature behind perpetual chaos. Stand at the edge of the ocean and take a breath. The weight of all the air above you creates a specific pressure on your body. Scientists call this one atmosphere, or 1 bar. It's the baseline we use to measure everything else. Go underwater and the pressure increases. Climb a mountain and it decreases. Simple enough on Earth, where we have solid ground to stand on. Now remove the ground entirely. Jupiter has no surface. Fly down into the planet and you'd pass through layers of gas, getting progressively thicker and hotter, until eventually the pressure turns hydrogen into liquid. Keep going, and that liquid becomes metallic, a strange state where hydrogen atoms are crushed so tightly they conduct electricity like metal. There's never a moment where you hit solid ground, no floor, no boundary, just continuous transformation from one state to another. When scientists needed to define Jupiter's size, they picked an arbitrary reference point, the 1 bar pressure level, the same pressure you experience breathing air at sea level. They decided that wherever Jupiter's atmosphere reaches that pressure, that's where we'll call the surface. It's an invisible line threading through clouds and storms, curving around the planet at different heights depending on local conditions. Jupiter's shape goes beyond a simple ellipsoid, like a slightly squashed ball. The density profile varies dramatically. Near the 1 bar level, density is less than water. At deeper levels, density reaches thousands of times that of water. Each layer responds differently to Jupiter's rotation and wind patterns. The result is a shape that deviates from a perfect ellipse by dozens of miles in different directions. Previous models tried to account for this using constant density assumptions. They pretended Jupiter was uniform enough to approximate as a simple geometric shape, close enough for government work, as the saying goes. Close enough turned out to be inadequate. The 1 bar level also shifts based on temperature. Warmer areas of atmosphere expand upward, pushing the 1 bar pressure line higher. Cooler areas contract, pulling it lower. Jupiter's bands of color represent temperature differences. which means the surface undulates like a wavy ocean frozen in place. Measuring that accurately requires knowing where the spacecraft is and what the temperature and pressure are doing at that exact moment in that exact location. Juno's radio occultation measurements solved this by creating detailed maps, comprehensive profiles showing how temperature, pressure, and electron density change with depth. These maps revealed something the earlier missions missed entirely. The winds at Jupiter's cloud tops extend deep into the planet, hundreds of miles down, creating what's called dynamical height variations. Essentially, the fast-moving jets push atmosphere outward through centrifugal force, creating bulges at the equator that earlier calculations underestimated. At the same time, slower-moving regions near the poles don't bulge as much, making the planet flatter than expected. When you add up all these wind-driven effects on top of rotation alone, you get a different planet than the one sitting in textbooks. A planet that's been hiding its true dimensions behind a storm that never stops. And those dimensions matter more than you might think. 8 kilometers. That's the gap between what we thought Jupiter's equator measured and what it actually measures. Convert that to miles, and you get about 5. 5 miles sounds trivial when you're talking about a planet with a radius of 44,000 miles. A rounding error, a blip, barely worth mentioning. The truth is different. Those missing miles represent a fundamental misunderstanding of how gas giants work. For scientists trying to model Jupiter's interior, the layers of liquid metallic hydrogen, the possible rocky core, the complex density gradients, those few miles make the difference between models that work and models that fail catastrophically. Think of it like baking a cake. If your measurements are off by a tiny percentage, the cake might still rise. It might still taste okay. When you're trying to understand the exact chemistry of how flour and eggs interact, that tiny error compounds. Your predictions about texture, moisture, and structure all drift further from reality. With Jupiter, scientists are trying to understand how gravity, rotation, and internal heat create the planet we observe. Small errors in the starting measurements cascade through every calculation. The polar measurements show even larger discrepancies. 12 kilometers flatter than previously thought. That's roughly 7.5 miles. For a planet as massive as Jupiter, being measurably flatter means the rotation and internal dynamics are distributing mass differently than models predicted. It suggests the deep interior might have different composition or temperature gradients than we assumed. Mayan Ziv, another researcher on the team, explained it clearly. The refined shape helps bridge the gap between models and measurements. Before these new dimensions, scientists had gravity data from Juno that didn't quite match the atmospheric observations. The numbers were close. The match was imperfect. That gap bothered researchers because it suggested either the gravity measurements were wrong, the atmospheric data was wrong, or the models themselves were missing something fundamental. Turns out the models were missing accurate dimensions. With the corrected size and shape, everything clicks into place. The gravity data makes sense. The atmospheric measurements align. The interior density models that describe how Jupiter transitions from gas to liquid to metallic states now fit the observations without needing exotic explanations. It's like finding the missing puzzle piece that makes the whole picture coherent. Here's the unsettling part. If we got Jupiter wrong, what about the other gas giants? Saturn, Uranus, and Neptune have all been measured using similar techniques. Older spacecraft, fewer data points, same assumptions about treating them as static objects. The Cassini mission gave us better Saturn data. Even that mission ended years ago. Uranus and Neptune haven't had dedicated orbiters at all. Our measurements come from brief flybys decades ago. The missing miles on Jupiter might be just the beginning. We might be carrying systemic errors in our understanding of every large planet in the solar system. Beyond that, every gas giant exoplanet we've detected around other stars was characterized using Jupiter as the reference standard. If the reference is wrong, the whole catalogue needs revision. Which brings us to an even bigger problem than most people realize. Jupiter rotates once every 9 hours and 55 minutes. That's fast. Absurdly fast for something so massive. Earth takes 24 hours to complete one rotation, and we're tiny compared to Jupiter. This rapid spin creates enormous centrifugal forces that fling material outward at the equator, creating the bulge every astronomy student learns about. Rotation alone doesn't tell the whole story. The winds tell it. Jupiter's atmosphere is carved into bands running parallel to the equator. Dark belts alternate with bright zones in a pattern that's held steady for as long as we've been watching. Those bands represent wind patterns, jet streams that race around the planet at speeds that would terrify any pilot. Some zones clock wind speeds over 400 miles per hour. That's faster than the strongest tornado ever recorded on Earth, and it never stops. Scientists knew about these winds. They've been photographing them for decades. What they didn't fully appreciate was how deep those winds go and how much force they generate. Previous models treated the winds as surface phenomena, skin-deep features riding on top of a more stable interior, like weather patterns on Earth that exist in the atmosphere without affecting the planet's shape. Jupiter's winds extend hundreds of miles down into the depths. Planetary-scale engines that large moving that fast create their own centrifugal forces independent of the planet's rotation. At the equator, where winds scream eastward at maximum velocity, those forces push the atmosphere outward, creating additional bulge on top of what rotation alone would produce. Near the poles, the winds behave differently. They're slower, more chaotic, less organized. They don't create the same outward push. The result is a planet that's flatter at the poles than simple rotation would suggest. The contrast between equatorial bulge and polar flattening is more extreme than basic physics would predict because the winds are actively reshaping the planet in real time. Yohai Caspi, who led the Weizmann team, emphasized this point. Earlier measurements didn't account for Jupiter's powerful winds. By incorporating those extreme wind dynamics into calculations, the team cleared up long-standing discrepancies in earlier measurements. Suddenly, the numbers made sense. The shape matched the forces. The models worked. This revelation changes how we think about gas giant planets fundamentally. They're dynamic systems where atmospheric processes actively shape the planet itself. The atmosphere is part of the planet's structure in a way that has no parallel on Earth. These massive worlds respond constantly to forces we're only beginning to understand. Consider what this means for other gas giants. Every massive planet with a thick atmosphere experiences similar dynamics. The winds on Saturn, Uranus, and Neptune also run deep. They also generate forces that reshape their host planets. We've been measuring all of them using models that ignore these effects, treating them like static objects that happen to have weather. We've been fundamentally misunderstanding how gas giants work. The consequences of that misunderstanding extend far beyond our solar system, because every gas giant exoplanet we found was compared to Jupiter, and Jupiter was wrong. Imagine if everything doctors knew about human anatomy came from examining 6 people, 6 bodies, 6 reference points. And from those 6 examples, medical science tried to extrapolate normal ranges for height, weight, organ size, blood pressure, everything. You'd trust that system right up until someone examined person number 7 and found different results. That's been Jupiter for 50 years. 6 measurements. 6 radio occultation experiments performed by Voyager 1, Voyager 2, Pioneer 10, and Pioneer 11 as they flew past the planet in the 1970s. Those 6 data points became locked into scientific literature as the measurements, capital T, capital M, the gold standard against which everything else was compared. Nobody questioned them. The missions were successful. The spacecraft functioned perfectly. The data looked clean. Multiple missions got similar results, which felt like confirmation. Add in the fact that those missions were heroic achievements, spacecraft traveling billions of miles through space to visit planets nobody had seen up close before, and questioning their data felt almost disrespectful. 6 measurements of a planet that changes shape based on wind patterns and rotation. 6 snapshots of a dynamic, churning atmosphere that never holds still. That's a starting point masquerading as a final answer. The problem compounds when you realize how radio occultation works. The spacecraft has to pass directly behind the planet, as seen from Earth. That geometry doesn't happen often, and when it does, it only gives you data for specific latitudes where the signal passes through. The Voyager and Pioneer missions flew by Jupiter on predetermined trajectories designed to reach other planets afterward. They couldn't linger. They couldn't optimize their paths for measurement opportunities. They got what they got and moved on. 6 measurements across a planet with a circumference of 273,000 miles at the equator. Do the math and you realize those data points are spread ridiculously thin. It's like trying to map Earth's terrain using 6 elevation measurements scattered randomly across the globe. You'd miss mountains, valleys, entire continents of variation. Yet those 6 measurements became scripture. Textbooks printed them. Research papers cited them. Planetarium shows displayed them. New students learned them by heart. Because they were internally consistent, because the models built from them seemed to work well enough, nobody pushed for better data. Jupiter was considered a solved problem. Measured, understood, done, until Juno showed otherwise. Juno didn't set out to prove the old measurements wrong. The spacecraft was designed to study Jupiter's interior structure, magnetic field, and atmospheric dynamics. Measuring the planet's exact size was almost a side project, something to nail down more precisely using modern technology. When those measurements started coming in during Juno's extended mission, they didn't match the textbook values. At first, researchers questioned their own data. Maybe the processing was wrong. Maybe there was systematic error in the new measurements. As more occultation opportunities occurred and more data accumulated, the pattern held. Jupiter was consistently smaller than expected, 26 measurements versus 6. The difference in statistical confidence is staggering. And it revealed something nobody wanted to admit. We'd been teaching the wrong numbers for half a century. Picture yourself standing behind a massive glass lens, the kind used in lighthouses or telescopes. As you move around, watching light pass through, you notice something. The light bends, it curves. The path changes depending on where you stand and what angle the light enters the lens. That bending follows precise rules based on the lens's shape and material. Jupiter's atmosphere is a lens, an enormous, turbulent, ever-changing lens made of hydrogen and helium instead of glass. When Juno passes behind Jupiter from Earth's perspective, the spacecraft's radio signal has to pass through this atmospheric lens to reach us. Just like light through glass, the signal bends. The bending follows rules. Radio waves travel at the speed of light in a vacuum. They slow down when passing through matter. The denser the matter, the slower they go. As the waves encounter layers of increasingly dense atmosphere, they bend toward the denser regions, the same way a beam of light bends when it enters water from air. By measuring exactly how much and in what direction the signal bends, scientists can calculate the density of the atmosphere at different depths. There's a trick to making this work. You need precise timing and positioning. The signal from Juno gets sent at a known frequency. As it passes through Jupiter's atmosphere, that frequency shifts slightly due to the bending, a phenomenon called Doppler shift. On Earth, massive radio dishes track these frequency changes with incredible precision, measuring shifts down to fractions of a hertz. The geometry has to be exact. Scientists know where Juno is to within a few meters thanks to careful tracking. They know where Jupiter is. They know where Earth is. With all 3 positions locked down, they can trace the exact path the radio signal takes. When that path intersects with Jupiter's atmosphere, the bending begins. The amount of bending reveals the atmospheric density at the intersection point. Here's what makes Juno special. The spacecraft's orbit takes it swooping down close to Jupiter's cloud tops, then swinging out far into space before returning. That elliptical path means sometimes Juno passes behind Jupiter at high latitudes near the poles, sometimes at mid-latitudes, sometimes near the equator. Each occultation samples a different slice of the planet, building up a three-dimensional map of atmospheric structure. The earlier missions couldn't do this. Their flybys were one-time events, quick visits on trajectories aimed at reaching Saturn, Uranus, and Neptune afterward. They got their measurements where geometry allowed and moved on. No orbital adjustments, no second chances. The 6 measurements they captured were valuable yet limited by circumstance rather than design. Juno orbits Jupiter permanently. Since the mission extension in 2021, it's been positioned to pass behind the planet regularly. Each orbit provides new opportunities. Each occultation adds data points. The spacecraft has already more than quadrupled the total number of radio occultation measurements ever taken of Jupiter. Those measurements show something the flybys couldn't reveal: variation. Jupiter changes. The atmospheric structure shifts with latitude. Temperature profiles differ between the equator and poles. Pressure gradients vary. Wind patterns create local distortions. You can't see that with 6 measurements. You need dozens, hundreds eventually. And what those dozens reveal is a planet we barely understood at all. 9 hours and 55 minutes. That's how long it takes Jupiter to complete one full rotation. For context, Earth needs 24 hours. Mars needs about 24 and a half. Even our moon, which is tidally locked to Earth and shows us the same face always, technically rotates once every 27 days. Jupiter does it in under 10 hours. Now consider the scale. Jupiter's equator spans 273,000 miles around. To complete one rotation in less than 10 hours, a point on the equator has to travel that entire distance, nearly the distance from Earth to the Moon, in the time it takes you to sleep through the night. Do the math, and you get speeds around 28,000 miles per hour at the cloud tops. That's 36 times faster than Earth's equatorial rotation speed. And Earth is much, much smaller. The forces involved are almost incomprehensible. Centrifugal force is what happens when something spinning tries to fling material outward. You feel it on a merry-go-round or when a car takes a sharp turn. The faster the spin, the stronger the outward pull. For Jupiter spinning at those speeds, the equator experiences enormous outward force trying to throw material into space. Only gravity holds it in place, creating a constant tug-of-war between rotation wanting to expand the planet and gravity wanting to compress it. The result is that bulge everyone learns about. Jupiter is noticeably wider at the equator than it is from pole to pole. The difference is almost 6,000 miles. That's substantial enough to see through a decent amateur telescope. Point a scope at Jupiter and you'll notice it looks slightly squashed, like someone pushed down on the top and bottom. What makes this interesting is the dynamic nature of that bulge, as different parts of the atmosphere spin at different speeds. Because remember, those bands of wind are moving faster or slower than the planet's average rotation. They create local variations in centrifugal force. Fast-moving equatorial jets add their own outward push. Slower polar regions don't push as hard. The overall shape becomes more complex than a simple oblate spheroid. It becomes a shape that responds to rotation, gravity, internal pressure, and atmospheric wind patterns all at once. Each factor influences the others. Faster rotation flattens the poles more. Flatter poles change how wind patterns organize. Changed wind patterns affect the bulge. It's a feedback loop with no simple solution. Previous models approximated this. They used equations that worked for simpler cases, solid bodies, uniform density, no massive atmospheric jets. Those approximations got close. Close enough that the errors weren't obvious without incredibly precise measurements. Close falls short of exact, and in planetary science, exact matters. The new measurements from Juno capture those complexities. They show how rotation and winds work together to shape the planet. They reveal that the simple equations don't quite cut it when you're dealing with something spinning this fast while being this large and this gaseous. Jupiter's rotation rate hasn't changed. The physics haven't changed. What changed is our ability to measure the consequences of that rotation accurately. And those accurate measurements are forcing us to rethink basic assumptions about planetary formation. Every planet spins, and every spinning planet bulges at the equator. Basic physics. Centrifugal force pushes material outward, gravity pulls it inward, and they reach an equilibrium that creates a slightly squashed sphere. For solid planets like Earth, this equilibrium is straightforward to calculate. You know the mass, the rotation rate, and the material properties. Plug those into equations, and out comes the shape. Gas giants break those simple rules. Jupiter has no solid surface to provide structural support. The entire planet is fluid, gas transitioning to liquid, transitioning to exotic metallic states under crushing pressure. Every layer responds to forces independently. The atmosphere doesn't care what the deep interior is doing. The deep interior doesn't care what the atmosphere thinks. Each finds its own equilibrium, and somehow all those independent layers have to stack together coherently. The textbook calculation for Jupiter's bulge used an assumption. It treated the planet as a body with a known average density that responds to rotation in a predictable way. Feed in Jupiter's mass, radius, and rotation period, and the equations spit out an expected amount of flattening. That expected value became the standard measurement because it matched what the Voyager and Pioneer missions reported. That calculation ignored atmospheric dynamics. When you have jet streams moving at hundreds of miles per hour, extending deep into the planet, they create additional centrifugal forces. A parcel of atmosphere racing eastward at the equator experiences more outward force than the planet's rotation alone would create. That pushes the 1 bar pressure level, remember, our definition of the surface, higher than it would be in a static atmosphere. Conversely, slower moving regions or areas with different wind patterns experience less force. The 1 bar level sits lower. The result is that the surface of Jupiter undulates based on wind patterns, creating a shape that's lumpier and more irregular than a perfect mathematical ellipse. Previous scientists knew about the winds. They could see them. They photographed them. Incorporating wind effects into planetary shape calculations is fiendishly difficult. You need to know how winds change with depth. You need to understand how they interact with the underlying rotation. You need computational models that can handle the complexity of a 3-dimensional fluid planet with temperature gradients, pressure gradients, and turbulent mixing all happening simultaneously. Those models didn't exist 50 years ago. The computing power didn't exist. Researchers made simplifying assumptions. They treated Jupiter as close enough to a static fluid body that the bulge would be mostly determined by rotation. The winds were considered secondary effects, minor perturbations that didn't change the big picture. Juno's data proved those assumptions wrong. The winds are major contributors to the planet's shape. Accounting for them changes the calculated dimensions by miles. And those miles matter because they cascade through every other measurement and model we use to understand Jupiter's interior. The bulge we thought we knew was an approximation, a useful one, still an approximation. The real bulge is messier, more dynamic, and harder to pin down with simple equations, which raises an uncomfortable question. What else are we approximating away? A computational model is a story told in mathematics. You take what you know, physical laws, observations, measurements, and translate them into equations. Then you ask a computer to solve those equations under different conditions to predict what you should see. If the predictions match reality, your model works. If they don't, something in your story is wrong. For Jupiter, the story scientists have been telling goes like this. The planet formed from the same cloud of gas and dust that created everything else in the solar system. Gravity pulled material together, creating an enormous ball of mostly hydrogen and helium. As more material accumulated, pressure and temperature in the core increased. Eventually, the core got hot enough and dense enough that the hydrogen entered exotic states, first liquid, then metallic. That metallic hydrogen layer is crucial. It conducts electricity and generates Jupiter's powerful magnetic field through a dynamo process similar to how Earth's liquid iron core creates our magnetic field. The models describe how thick that metallic layer is, what temperature and pressure exist at different depths, and how the transition from gas to liquid to metal happens. Models are only as good as their inputs. If you tell the model that Jupiter's radius is 44,423 miles at the equator, it builds its density profiles based on that number. Every layer inside the planet gets calculated relative to that outer boundary. The pressure gradients, temperature gradients, composition changes, all of them depend on knowing where the surface is. When the surface moves by several miles, everything below shifts. It's like building a house on what you think is level ground, then discovering the foundation is actually tilted. The house might still stand. It might even function. The stresses on the walls differ from what you calculated. The load-bearing beams carry different weights than intended. Small initial errors create bigger problems as you build upward. For Jupiter's models, the corrected dimensions solved a persistent puzzle. Juno's gravity measurements, which come from tracking tiny changes in the spacecraft's orbit caused by mass distribution inside Jupiter, didn't quite match what the atmospheric observations suggested. The numbers were close. The match was imperfect. That mismatch bothered researchers because it implied either the gravity data was wrong, the atmospheric data was wrong, or the interior models were missing something. With the new dimensions plugged in, the mismatch disappeared. The gravity data now aligns with atmospheric observations. The interior density models work without needing exotic explanations like unexpected composition variations or anomalous temperature profiles. Everything fits together cleanly. The story the models tell now matches the measurements we can actually make. Eli Galanti described it precisely. Shifting the radius by just a little lets models of Jupiter's interior fit both the gravity data and atmospheric measurements much better. Those few kilometers matter. They're the difference between a model that sort of works and a model that actually works. Since Jupiter serves as the template for understanding gas giants everywhere, in our solar system and around other stars, getting these models right has implications far beyond one planet. Because if our models of Jupiter were subtly wrong for 50 years, what about our models of everything else? Right now, in classrooms around the world, teachers are showing students diagrams of the solar system. Those diagrams include Jupiter with specific measurements. 88,846 miles across at the equator, 83,082 miles from pole to pole. Students memorize these numbers for tests. They cite them in papers. They carry them forward as established fact. All of those numbers are wrong. The error is small. The error matters. It's significant enough that Yohai Caspi, one of the lead researchers, stated bluntly that textbooks will need updating. In science, that's a significant admission. Textbooks don't change casually. They represent consensus knowledge. Facts considered so well established that they're suitable for teaching the next generation. Changing textbook values means admitting a fundamental measurement error persisted for decades. The practical impact might seem small. Most people will never need to know Jupiter's exact radius. Amateur astronomers can still observe the planet through telescopes. NASA can still send missions there. Spacecraft navigation already uses more sophisticated models than what appears in introductory textbooks. Life goes on. Symbolically, this matters tremendously. Jupiter is the solar system's flagship planet, the largest world, the most massive, the one with the most moons, the first gas giant. It appears in every astronomy curriculum, from elementary school through graduate programs. If we got something as basic as its size wrong for 50 years, what message does that send about the reliability of scientific knowledge? It sends exactly the right message, actually. Science is self-correcting. When better measurements become available, we update our understanding. We don't cling to old numbers out of pride or tradition. We acknowledge errors, make corrections, and move forward. That's how the process is supposed to work. The textbook rewrites are already beginning. Publishers have been notified. Database managers are updating astronomical reference tables. Planetarium software will get patches. Educational materials will be revised. It's a slow process because printed textbooks don't turn over quickly. Within a few years, students will learn the new numbers instead of the old ones, and they probably won't realize anything changed. That's both good and bad. Good because it means the correction happens smoothly without causing confusion. Bad because it obscures how science actually works through constant refinement, questioning assumptions, and improving measurements. Students might graduate thinking we've always known Jupiter's exact size, never learning that this fact was recently corrected after half a century. The deeper lesson here goes beyond Jupiter's dimensions. It's about epistemic humility, the willingness to say we measured this as carefully as we could with the tools available, and better tools might reveal our measurements were imperfect. That humility is what separates science from dogma. Jupiter didn't shrink. Our understanding expanded. The measurements improved. The models got better. The story we tell about gas giants became more accurate. And that's worth updating every textbook in existence. Because if one thing is certain in astronomy, it's this: we're not done discovering surprises, especially when it comes to what these new measurements mean for planets beyond our solar system. We've discovered over 5,000 planets orbiting other stars. 5,000 worlds out there in the galaxy, each one catalogued with measurements: mass, radius, density, orbital period. Scientists use these numbers to classify planets. Is it rocky, like Earth? Gaseous, like Jupiter? Somewhere in between? Every single one of those classifications depends on knowing how big Jupiter actually is. Here's why. When astronomers detect an exoplanet, they rarely see it directly. Most discoveries come from watching a star dim slightly as a planet passes in front of it. The amount of dimming tells you how much area the planet blocks, which reveals its size relative to the star. To translate that into actual dimensions, you need reference points. You need to know how big a Jupiter-sized planet should be. For decades, that reference was wrong. If Jupiter is smaller than textbooks claimed, then every exoplanet we compared to Jupiter needs recalibration. A world we classified as slightly larger than Jupiter might actually be significantly larger. A planet we thought was Jupiter-sized might be smaller. The entire catalogue shifts. Academic hair-splitting? Far from it. Planet classification drives research priorities. Scientists get excited about finding Earth-sized planets in habitable zones because those might support life. They study super-Earths, rocky worlds larger than ours and smaller than Neptune, because they represent a planet type missing from our solar system. Gas giants like Jupiter interest us for different reasons, helping us understand planetary formation and system architecture. Misclassifying planets means misunderstanding which worlds deserve closer study. The correction propagates through everything. Density calculations change because density equals mass divided by volume. If the volume is different than we thought, density shifts. And density tells us what a planet is made of. High density suggests rock and metal. Low density indicates gas. Medium density points to water or ice. Get the size wrong, and you might think an icy world is rocky, or vice versa. Atmospheric studies get affected too. The thickness and composition of a planet's atmosphere depend partly on surface gravity, which depends on mass and radius. Change the radius, and you change your predictions about what gases the planet can hold on to. Hydrogen escapes easily from small planets. It stays trapped on large ones. If your size estimate is off, your atmospheric models drift. The James Webb Space Telescope is currently studying exoplanet atmospheres in unprecedented detail. It's looking for chemical signatures, water vapor, methane, carbon dioxide, that might indicate habitability or even life. Those observations get interpreted using models built on our understanding of how planets work. Models calibrated against Jupiter. If the calibration is wrong, the interpretations might be wrong. Paul Robertson, a researcher working with exoplanet data, acknowledged this directly. The revised Jupiter measurements have important implications for understanding exoplanets, including prioritization for follow-up observations with James Webb. We might be pointing our most powerful telescope at the wrong targets because we've been categorizing planets incorrectly. The universe didn't change. Our measurements did. Those measurements determine which mysteries we chase next, and which ones we might be overlooking entirely. The TESS Space Telescope has revolutionized exoplanet hunting. Launched in 2018, it scans the sky looking for planets around nearby stars. Its mission is finding small worlds, Earth-sized planets, maybe slightly larger, that could potentially harbor life. TESS has discovered hundreds of candidates, worlds that scientists eagerly categorize and study. Some of those worlds might be something different than we think. TESS detects planets using the transit method. When a planet crosses in front of its star from our perspective, the star's brightness drops slightly. The amount of dimming depends on the planet's size. A bigger planet blocks more light, creating a deeper dip. By measuring that dip precisely, astronomers calculate the planet's radius. Here's the problem. The calculation requires knowing how big the star is, because you're measuring the planet as a fraction of the star's size. Measuring stars involves comparing them to models. Models built using our solar system as the reference frame. Models that assume we know how big planets like Jupiter actually are. The correction to Jupiter's size cascades backward through those stellar models. If gas giants are systematically smaller than we thought, then our models of how stars and planets relate need adjustment. That adjustment changes our estimates for star sizes, which changes our estimates for planet sizes derived from transit measurements. Sky and Telescope magazine reported the implications bluntly. Only 3 of the single-planet systems found by TESS so far were marked as similar in size to our planet. Now, all of them are likely bigger, perhaps super-Earths, instead of genuine Earth analogues. Some might even turn out to be larger gaseous planets, more similar to Uranus and Neptune than Earth. Think about what that means. Scientists search for Earth-like worlds because they're potentially habitable. Rocky planets with solid surfaces where liquid water might exist, where atmospheres could develop, where life might emerge. Super-Earths complicate that picture. They're bigger, with stronger gravity. They might have thick hydrogen atmospheres that make the surface uninhabitable. Or they might be mini-Neptunes, ice giants with no solid surface at all. The difference matters enormously for astrobiology. A planet that looks Earth-sized yet turns out to be a super-Earth, or mini-Neptune, probably lacks habitable conditions we understand. It won't have landscapes and oceans like Earth. It won't experience similar atmospheric conditions. The search for life requires finding planets genuinely comparable to ours, worlds that superficially resemble Earth while fundamentally differing. TESS faces this challenge now. Every exoplanet catalogue built over the past 2 decades relied on the same reference standards. The same assumptions about Jupiter's size filtering through stellar models into planetary measurements. Kepler discovered thousands of planets before TESS launched. Those measurements need revisiting too. The corrections might be small. We're talking percentage point differences in most cases. When you're trying to distinguish between an Earth-sized planet and a super-Earth, those percentage points matter. They determine whether a world gets flagged for follow-up study with James Webb or gets passed over in favor of more promising candidates. We thought we were getting better at finding Earths. Turns out, we were getting better at finding planets we mistakenly thought were Earths. And the implications extend beyond just size estimates into questions about habitability itself. Recalibrating thousands of exoplanet measurements sounds straightforward in principle. You take the old data, apply the correction factor from Jupiter's revised dimensions, and generate new values. Simple math. Computers can handle it in seconds. Reality is messier. The correction varies across all planets. It depends on how each planet was measured, what comparison stars were used, what models were applied. Some measurements relied more heavily on Jupiter as a reference than others. Some used different calibration methods entirely. You can't just multiply everything by a correction factor and call it done. Each planet requires individual analysis. Scientists need to go back through observation data, some of it decades old, and reprocess it using updated models. That means retrieving archived telescope data, running it through modern software, cross-checking results against multiple reference standards. It's time-consuming work that offers no glory. You don't win awards for correcting someone else's measurements. You don't get headlines for making things slightly more accurate. The work has to happen anyway. The TESS mission presents a particular challenge because it's still actively discovering new planets. Every few months, TESS announces fresh candidates. Those announcements include size estimates based on current models. If the models are being revised in real time as Jupiter data improves, then planets announced last year might use different standards than planets announced next month. Consistency becomes problematic. Imagine comparing two planets discovered a year apart only to realize they were measured using incompatible baselines. One used the old Jupiter reference, one used the new. Their relative sizes become ambiguous. Which measurement do you trust more? Do you reprocess the older one to match the newer standard? Do you wait for both to be reprocessed uniformly? These are more than technical annoyances. They affect scientific conclusions. If a researcher is studying how planet sizes correlate with orbital distances, using inconsistent measurements introduces errors into the correlation. If someone is investigating whether certain types of stars preferentially host certain types of planets, mixed calibration standards muddy the patterns. Statistical analysis requires consistent data sets. Mixing old and new measurements without careful accounting creates false signals. The astronomical community is working through this now. Papers are being published with revised exoplanet catalogues. Database maintainers are updating their entries. Mission teams are reprocessing archived observations. It's happening. It takes time, years potentially. Meanwhile, new observations keep coming in. James Webb continues studying exoplanet atmospheres. Ground-based telescopes keep finding new worlds. The European Space Agency's Plato mission is scheduled to launch soon, adding even more discoveries. All of these efforts build on the foundation of existing exoplanet knowledge that's currently being revised. It's like trying to build a house while the foundation is being repaired. You can keep building. You have to stay aware that the base might shift. Conclusions drawn today might need revision tomorrow, once all the calibrations settle. Science is supposed to be cumulative. Each discovery builds on previous discoveries, creating an ever-growing edifice of knowledge. Sometimes you have to pause the building to fix the foundation. Right now, with Jupiter's true size finally nailed down, we're fixing foundation we didn't know was cracked, which forces us to ask what else might be cracked that we haven't noticed yet. Beneath Jupiter's clouds lies a mystery we can't directly observe. No spacecraft will ever land on Jupiter to dig down and sample the interior. The pressure and heat would destroy any probe long before it reached interesting depths. Everything we know about what's inside comes from inference, from measuring how gravity behaves, from modeling how matter responds to extreme conditions, and from knowing exactly where the surface is. Jupiter's interior structure follows a progression dictated by pressure. At the cloud tops, where we can see, hydrogen and helium exist as gases. Descend deeper and pressure increases. Temperature rises. Eventually, the pressure becomes so intense that hydrogen stops behaving like a gas and starts behaving like a liquid. Through compression alone, the atoms get squeezed together until they flow. Go deeper still, and things get truly exotic. At pressures millions of times greater than Earth's atmosphere, hydrogen enters a state called liquid metallic hydrogen. The electrons get stripped away from atoms, creating a sea of charged particles that conducts electricity like metal. This layer generates Jupiter's powerful magnetic field through dynamo action, swirling metallic hydrogen, creating electric currents, creating magnetic fields. At the very center, there might be a rocky core. Models suggest it could be 10 to 20 times Earth's mass, composed of rock and ice compressed to unimaginable densities. The core is speculative. We can't see it. We can barely detect it gravitationally. All of these layers stack together to create the planet we observe. Each layer has a specific density, temperature, and pressure. The boundaries between layers occur at specific depths where the physics changes. All of those depths are measured relative to the surface. Move the surface and everything shifts. The corrected dimensions from Juno revealed something subtle yet important. The interior models that best matched the new size measurements showed slightly different density gradients than previous models. The transition from gaseous to liquid hydrogen happens at a different depth. The liquid metallic hydrogen layer is thicker or thinner than earlier estimates suggested. The possible core might be smaller. These are refinements. Jupiter didn't suddenly develop a completely different interior. The refinements matter for understanding planetary formation. How did Jupiter accumulate its mass? Did it form quickly by gobbling up gas before the early solar system dispersed? Or did it grow more slowly, building a rocky core first and then pulling in atmospheric gases later? The interior structure holds clues. A large, dense core suggests slow formation with solid materials accumulating first. A small or diffuse core points toward rapid gas accretion. The density profile tells you how thoroughly the planet mixed during formation. Layered structures indicate incomplete mixing. Smooth gradients suggest thorough convection. With accurate measurements, scientists can distinguish between these scenarios. They can test different formation theories against real data instead of relying on approximations. They can ask questions like, does Jupiter's core rotate at a different rate than its atmosphere? Are there stable layers that prevent mixing? How much heat is Jupiter still generating from its formation billions of years ago? The answers were always there, hidden in the measurements. We were measuring carefully enough to see them only now. And now that we can, the picture of Jupiter's interior is finally coming into focus. Gravity is a sensitive tool. Fly a spacecraft near a planet, and the planet's gravity tugs on it. The strength of that tug depends on how much mass is nearby. Denser regions pull harder. Less dense regions pull more weakly. By tracking tiny changes in a spacecraft's velocity and trajectory, scientists can map the distribution of mass inside a planet. Juno carries instruments designed precisely for this. As the spacecraft orbits Jupiter, ground stations on Earth track its radio signals with extraordinary precision. They measure Doppler shifts, changes in signal frequency caused by the spacecraft speeding up or slowing down as Jupiter's gravity pulls on it. Those shifts reveal how gravity varies across different parts of the planet. The data showed something puzzling. The gravity field didn't quite match what the atmospheric observations suggested. If you calculated Jupiter's interior structure based on what Juno saw in the clouds, the temperature patterns, the wind speeds, the visible features, and then predicted what the gravity field should look like, You got numbers that were close to measurements, yet imperfect. The discrepancy was small. It was persistent. No matter how researchers adjusted their models, they couldn't make the gravity data and atmospheric data agree perfectly. Something was off. Scientists considered various explanations. Maybe the atmospheric observations were misinterpreted. Maybe the cloud features didn't actually indicate what we thought they indicated about deeper winds. Maybe the gravity instruments had systematic errors nobody had identified. Maybe Jupiter's interior was weirder than standard models allowed, perhaps with unexpected composition variations or strange mixing patterns. Or maybe the dimensions were wrong. When the corrected size measurements came in, researchers plugged them into the models. The gravity predictions changed by just enough. Suddenly the numbers aligned. The gravity field Juno measured matched what you'd expect from a planet, with the observed atmospheric features and the newly determined size and shape. The discrepancy vanished. It's like trying to balance a complex equation where one variable is slightly off. You keep adjusting other variables trying to make things work. Nothing quite fits. Then you realize your initial value was wrong. Correct that one number and everything else falls into place naturally. For planetary science, this validation is crucial. It means the models work, the physics is sound. Our understanding of how gas giants behave under extreme conditions is accurate. We weren't missing some exotic phenomenon or fundamental process. We were just measuring from the wrong baseline. This gives confidence for future work. When the European Space Agency's JUICE mission arrives at Jupiter in the 2030s, it will carry even more sophisticated instruments. Those instruments will map Jupiter's interior in greater detail than ever before. Scientists can now trust that the interpretations of that data will be built on solid foundations. The gravity data was trying to tell us something all along. It was saying our size measurements didn't match reality. We just needed better measurements to hear the message clearly. Now that we have them, the story of Jupiter's interior is finally coherent. And coherence reveals patterns we couldn't see before. Look at any image of Jupiter, and you'll see stripes. Dark bands alternating with bright zones running parallel to the equator. Those stripes are winds. Massive rivers of atmosphere flowing in opposite directions at different latitudes. They're permanent features shaped by forces we're only beginning to understand. The technical term is zonal winds. Zonal means they run east-west rather than north-south. Some zones flow eastward, racing ahead of the planet's rotation. Others flow westward, moving backward relative to the spin. The shear between adjacent zones creates turbulence, the chaotic mixing that generates Jupiter's famous storms. These winds don't just skim along the surface. They penetrate deep into the planet, thousands of miles down. Juno's gravity measurements revealed this. By detecting subtle variations in gravitational pull, scientists mapped how mass is distributed inside Jupiter. The data showed that wind patterns visible at the cloud tops extend downward to depths of about 3,000 miles before dissipating. 3,000 miles of atmosphere moving at hundreds of miles per hour creates forces that rival planetary rotation itself. When a parcel of air rushes eastward at 400 miles per hour, it experiences centrifugal force trying to fling it outward. That force adds to the outward push from the planet's rotation. The combined effect pushes the 1 bar pressure level higher than it would be in a calm atmosphere. The planet physically bulges more at latitudes where eastward winds are strongest. Conversely, westward flowing zones experience reduced centrifugal force. They push outward less than the planet's rotation alone would suggest. The 1 bar level sits lower. The overall effect is that Jupiter's shape becomes latitude dependent, a simple ellipse with undulations following the wind pattern rather than a perfect geometric form. Previous models didn't account for this because they treated the atmosphere as a thin skin, a surface layer that might affect weather without significantly influencing the planet's bulk shape. That assumption works for Earth, where the atmosphere is a few dozen miles thick on a planet 8,000 miles in diameter. The atmosphere is negligible compared to the solid planet beneath. Jupiter has no solid planet beneath. Its atmosphere all the way down, transitioning smoothly into liquid and then metallic states. The atmosphere is the planet. When that atmosphere contains wind patterns extending thousands of miles deep, those patterns shape the entire structure. The corrected measurements captured this. By incorporating wind effects into shape calculations, scientists derived dimensions that actually match observations. The dynamical height variations, the way winds push and pull on the atmosphere, creating local bulges and depressions, are now part of the standard model. This changes how we think about atmospheric dynamics on gas giants. The atmosphere actively reshapes the world in real time. There's no clear boundary between atmosphere and interior, no line where the planet ends and the weather begins. Jupiter is a fluid system all the way through. Understanding that fluidity required measuring carefully enough to see the signature of winds in the planet's very shape. A signature that's been there all along, waiting for instruments precise enough to detect it. And now that we can see it, new questions emerge about what else might be hiding in plain sight. The Voyager missions stand among humanity's greatest achievements. 2 spacecraft launched in 1977 on a grand tour of the outer solar system. They visited Jupiter, Saturn, Uranus, and Neptune. They sent back the first close-up images of these worlds. They discovered new moons. They revealed planetary ring systems. They revolutionized our understanding of the solar system. They couldn't do radio occultation of Jupiter the way Juno does. The reason comes down to orbital mechanics. Voyager 1 and 2 were designed for flybys, high-speed passes that used Jupiter's gravity to slingshot them towards Saturn. The trajectory had to be precise. Too high, and they'd miss the gravitational assist. Too low, and they'd crash. The path was optimized for reaching the next destination rather than for studying Jupiter comprehensively. Radio occultation requires the spacecraft to pass directly behind the planet, as seen from Earth. That geometry depends on the spacecraft's trajectory relative to both Jupiter and Earth. During a flyby lasting a few days, you get limited opportunities, maybe 1 or 2 occultations if you're lucky. The Voyagers got their measurements where chance allowed and moved on. Pioneer 10 and 11 had similar constraints. They were the first spacecraft to visit Jupiter, arriving in 1973 and 74. Like the Voyagers, they performed flybys optimized for survival and data collection during brief encounters. Getting multiple occultation measurements from different latitudes was never part of the mission design. Between the 4 spacecraft, 6 total occultation measurements. That's what was possible given the technology and mission constraints of the 1970s. Juno changes everything by orbiting Jupiter permanently. The spacecraft arrived in 2016 and will remain there until its mission ends. That gives hundreds of orbits, hundreds of chances to position the spacecraft for occultation opportunities. The mission team can plan observations systematically instead of hoping geometry aligns during a brief flyby. Even Juno's original orbit didn't allow this. The spacecraft followed a highly elliptical path designed to keep it away from Jupiter's intense radiation belts most of the time. That orbit took Juno over Jupiter's poles, great for studying the magnetic field and polar dynamics. Less ideal for radio occultation, which requires passing behind the planet from Earth's perspective. The breakthrough came with the mission extension in 2021. Juno's orbit was adjusted to bring it closer to Jupiter's equatorial plane and to time its passes so they occasionally occurred behind the planet. That adjustment unlocked the occultation measurements that revealed Jupiter's true size. Technology mattered too. Modern radio receivers on Earth can track frequency shifts with precision impossible in the 1970s. Computational power lets scientists process massive data sets and run sophisticated atmospheric models. Juno's instruments provide real-time data on Jupiter's gravity, magnetic field, and atmospheric composition that help calibrate the occultation measurements. Earlier scientists worked with what they had. They made brilliant measurements given the constraints. Those measurements stood unchallenged for 50 years because they were internally consistent and nobody had better data. Now we do. And that better data is forcing us to reconsider everything we thought we knew about measuring planets, about what we can trust and what needs verification. Juno was supposed to die in February 2018. That was the plan. The spacecraft would complete its primary mission studying Jupiter's magnetic field, gravity, and atmospheric composition, then deliberately crash into the planet to avoid contaminating any of Jupiter's moons with Earth microbes. Clean ending. Mission accomplished. NASA extended it instead. The decision came from practical considerations. Juno's instruments were still functioning perfectly. The spacecraft had fuel remaining. The science team had ideas for additional investigations. Jupiter's moons, particularly the volcanic moon Io and the ice-covered Europa, offered compelling targets. Extending the mission made sense for maximizing the return on a multi-billion-dollar investment. The extension required changing Juno's orbit. The original trajectory kept the spacecraft in a polar orbit, passing over Jupiter's north and south poles every 53 days. Great for studying magnetic fields and auroras. Less useful for close encounters with equatorial moons. The extended mission adjusted the orbit to allow targeted flybys of Ganymede, Europa, and Io. That adjustment had an unintended consequence. It put Juno on a path that occasionally passed behind Jupiter from Earth's perspective. Nobody planned this for radio occultation measurements. The trajectory change was about getting close to moons. Once scientists realized the new orbit created occultation opportunities, they jumped on them. Suddenly Juno could do something the Voyager and Pioneer missions never managed: systematic measurements of Jupiter's size from multiple latitudes over multiple orbits. The first few occultations happened almost by accident. Scientists processed the data more out of curiosity than expectation. When the results came back showing Jupiter was slightly smaller than textbook values, the initial reaction was skepticism. Maybe something was wrong with the processing. Maybe there was interference in the signal. More occultations produced the same results. The pattern held. Jupiter was consistently measuring smaller than expected. The team developed specialized techniques for processing the data, accounting for atmospheric turbulence and wind effects. Maria Smirnova's analysis methods extracted incredibly precise measurements from the radio signals. 26 successful occultations later, the evidence was overwhelming. Measurement error? No. Reality revealed. If Juno's mission had ended on schedule in 2018, we might still be using the wrong dimensions for Jupiter. The discovery required both the extended mission and the specific orbital adjustments made for moon flybys. Neither alone would have been sufficient. You needed both the time and the trajectory. It's a reminder that space missions often produce their most important discoveries in unexpected ways. Voyager discovered active volcanoes on Io while trying to photograph Jupiter's moons. Cassini found water geysers on Enceladus during a routine flyby. Hubble detected the accelerating expansion of the universe while measuring distant supernovae for a completely different purpose. Science rewards prepared minds and flexible missions. Juno was prepared with instruments capable of precise radio occultation measurements. The extended mission provided the flexibility to exploit those capabilities in ways nobody initially planned, and Jupiter revealed its true size to spacecraft that was looking elsewhere. Sometimes the most important questions get answered while you're pursuing something else entirely. And sometimes, fixing one measurement opens up questions we never thought to ask. Questions about what else we've been getting wrong all along. Forget the technical jargon for a moment. Here's what actually happens during a radio occultation measurement. Juno has a radio transmitter. It beams signals toward Earth constantly, partly for communication and partly for navigation. On Earth, massive dish antennas, some of them over 200 feet across, track those signals with incredible precision. They measure whether the signal is there and exactly what frequency it's transmitting at. As Juno moves through space, The frequency shifts slightly due to the Doppler effect, same phenomenon that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it drives away. When Juno moves toward Earth, the radio waves get compressed, increasing frequency. When it moves away, they get stretched, decreasing frequency. Scientists know exactly how fast Juno should be moving based on Jupiter's gravity and the spacecraft's orbit. They can predict what Doppler shift to expect. When the observed shift matches predictions, everything is normal. When it doesn't match, something is affecting the signal. Jupiter's atmosphere is that something. As Juno passes behind Jupiter, its radio signal has to travel through progressively denser layers of atmosphere to reach Earth. Dense atmosphere slows down radio waves. Slower waves mean longer wavelength, which translates to lower frequency. The signal shifts in ways that gravity and orbital mechanics alone can't explain. By measuring how much extra shift occurs and when, scientists can map the density of Jupiter's atmosphere at different altitudes. They know where Juno is. They know where Earth is. They can calculate the exact path the radio signal takes. Where that path intersects Jupiter's atmosphere, the bending and slowing reveal atmospheric properties. Think of it like echolocation. Bats send out sound waves and listen for how those waves bounce back or get absorbed. The pattern tells them what's in the environment. Radio occultation does something similar, sending waves through an atmosphere and analyzing how they get modified. The technique is sensitive enough to detect temperature changes of less than 1 degree, pressure variations of a fraction of a percent, electron densities that indicate ionized regions high in the atmosphere, all from analyzing subtle frequency shifts in a radio signal traveling hundreds of millions of miles. There's a catch. The measurement only works during the brief period when Juno passes behind Jupiter. The geometry has to be exactly right. Too high, and the signal passes over Jupiter's atmosphere without intersecting it. Too low, and the bulk of the planet blocks the signal entirely. There's a sweet spot, a few thousand miles of altitude, where the signal grazes through the atmosphere before cutting out. Each occultation lasts maybe 30 minutes. In that half-hour window, the signal sweeps through different layers, sampling atmosphere at various depths. The data comes in as a continuous stream of frequency measurements. Post-processing turns those measurements into temperature and density profiles. 26 successful occultations provided 26 profiles at different latitudes: equatorial regions, mid-latitudes, near the poles. Each one added detail to the picture of Jupiter's shape and structure, and each one confirmed that the planet is smaller than we thought. Simple concept, sophisticated execution, revolutionary results that are still unfolding. Temperature and pressure are connected. Heater gas and pressure increases, compressor gas and temperature rises. This relationship governs everything from car engines to weather systems to the interiors of planets. On Jupiter, understanding this relationship means understanding how the planet works. Measuring temperature and pressure inside Jupiter's atmosphere is nearly impossible with conventional methods. You can't drop a thermometer into those clouds. Any probe would be crushed and melted long before reaching interesting depths. The only option is remote sensing, measuring from a distance using clever techniques. Radio occultation provides that technique. As radio waves travel through Jupiter's atmosphere, they bend. The amount of bending depends on atmospheric density. Density connects to both temperature and pressure through known physical laws. If you measure how much the signal bends at different altitudes, you can work backward to calculate the temperature and pressure at each altitude. The math gets complex. The principle is straightforward. Warm gas at a given pressure is less dense than cold gas at the same pressure. By measuring density and knowing the pressure level you're observing, remember, the 1 bar level is our reference point. You can calculate temperature. Similarly, if you know temperature and density, you can derive pressure. Juno's occultation measurements created 3-dimensional maps. entire vertical profiles showing how temperature and pressure change from the cloud tops down to depths where the atmosphere transitions to liquid. These maps revealed structure nobody had seen before. Equatorial regions showed one temperature profile. Mid-latitude regions showed another. Polar areas were different still. The variations correlate with wind patterns. Fast-moving jets create different temperature signatures than slow-moving zones. The Great Red Spot, Jupiter's massive storm, produces its own distinct profile. Temperature gradients drive atmospheric circulation. Hot air rises, cold air sinks, and the motion creates weather. On Earth, this circulation is relatively simple. Warm tropical air rises, moves toward the poles, cools, and sinks. That basic pattern gets modified by continents, oceans, and Earth's rotation. The fundamentals are straightforward. Jupiter has no continents or oceans to complicate things. It has those deep wind patterns, thousands of miles of atmospheric depth, all in motion. The temperature maps show how heat flows through this system, where internal heat from the planet's formation bubbles up, where solar radiation heats the upper atmosphere, where zones of rising warm air and sinking cool air organize into the band structure we observe. Previously, scientists could only guess at these patterns based on what they saw at the cloud tops. The occultation data revealed what's happening beneath the visible surface. It showed that the wind patterns are part of a deep convective system that extends far into the planet. The temperature and pressure maps also helped validate the size measurements. If the 1 bar pressure level sits at a different altitude than expected, the temperature at that altitude will differ from predictions. The occultation data showed consistent results. The 1 bar level is where the new measurements place it, and the temperatures there match what you'd expect for Jupiter's overall heat budget. Everything fits together. The size, the shape, the temperature structure, the pressure profiles, it's all coherent. Finally, after 50 years, we're seeing Jupiter clearly. And seeing clearly reveals how much we still don't understand. Jupiter serves as the reference point for gas giants everywhere. When astronomers discover a new exoplanet and describe it as Jupiter-sized, they mean it's approximately as large as Jupiter. When planetary formation theories predict what happens when a certain amount of gas accumulates, they use Jupiter as the test case. When physicists model how hydrogen behaves under extreme pressure, they calibrate against Jupiter's interior. If Jupiter is wrong, all of those comparisons are wrong. This creates what scientists call a systematic error, random noise that averages out with more measurements. No, a consistent bias affecting every observation in the same direction. You can collect 1 million data points. If your ruler is miscalibrated, all million measurements will be off by the same amount. For decades, that's what we've been doing, measuring everything against a Jupiter that was slightly larger than reality. The error propagated through the entire field of planetary science like a crack spreading through glass. Consider how this affects our understanding of planetary formation. The prevailing theory says gas giants form when a rocky core accumulates enough mass to gravitationally capture huge amounts of hydrogen and helium from the surrounding nebula. The size of the resulting planet depends on how much gas gets captured and how efficiently it settles into a stable configuration. Models of this process are calibrated against Jupiter. They're designed to produce a planet with Jupiter's mass and size. If you input conditions similar to the early solar system, the model should output something Jupiter-like. That's how you know the model works. The model was calibrated to produce the wrong size. Does that mean the formation theory is wrong? Maybe. Maybe the theory is correct and the parameters need adjustment. Maybe gas capture was slightly less efficient than models suggested. Maybe the core was larger. Maybe the temperature distribution in the early solar system was different. Tweaking these parameters can make the model produce a smaller Jupiter, or maybe the theory needs more fundamental revision. This is why reference standards matter so much in science. When everyone uses the same reference, Errors in that reference affect everyone's work. It creates false consensus. Multiple independent studies all reach similar conclusions because they're all using the same flawed starting point, rather than because they're all correct. The gold standard problem appears throughout scientific history. Atomic weights were wrong for decades because the reference standard for carbon was miscalibrated. Stellar distances were off because the parallax measurements used as references had systematic errors. The speed of light was gradually refined over centuries as measurement techniques improved. Each time a fundamental reference gets corrected, it forces re-evaluation of everything built on that reference. We're in that re-evaluation period now for planetary science. Jupiter was our gold standard, the planet by which all others were measured. The discovery that it's smaller than we thought means examining every measurement and model that used it as a reference. Some will survive the re-evaluation unchanged. Others will need revision. A few might be fundamentally wrong. The process is necessary. You can't build accurate science on inaccurate foundations. Now that the foundation is corrected, we can build something better, something that might actually match the universe as it truly is. Uranus and Neptune are the solar system's forgotten giants. Jupiter and Saturn get all the attention, largest planets, spectacular rings, dozens of moons. Uranus and Neptune orbit so far away that they're barely visible to the naked eye. Only one spacecraft has ever visited them, Voyager 2, during brief flybys in 1986 and 89. Everything we know about their size comes from those flybys. Sound familiar? The same technique used to measure Jupiter, Frodio occultation, during a spacecraft flyby, provided our measurements for Uranus and Neptune. The same limited dataset, the same assumptions about atmospheric structure, the same lack of comprehensive coverage across multiple latitudes. If Jupiter's measurements were wrong, what about theirs? Uranus and Neptune are ice giants, planets with rocky cores surrounded by thick mantles of water, methane, and ammonia ices, topped with relatively thin atmospheres of hydrogen and helium. The internal structure differs significantly from Jupiter. The physics governing their shape follows different rules. The measurement technique is the same. Radio signals bending through atmospheres, scientists calculating planet dimensions based on signal deflection. Just like with Jupiter, those measurements assumed the atmosphere was relatively static, ignoring deep wind effects or complex pressure variations. Uranus presents particular challenges. The planet rotates on its side, its axis tilted 98 degrees compared to its orbital plane. This bizarre orientation creates extreme seasonal variations. One pole points toward the solar neighborhood for 42 years straight, then darkness for 42 years. The atmospheric dynamics are unlike anything else we've observed. Neptune has the solar system's fastest winds. Speeds exceeding 1,200 miles per hour have been clocked in its atmosphere. Storms appear and disappear on timescales of months. The planet emits more heat than it receives from the distant stellar center, suggesting active internal processes churning beneath the clouds. Both planets likely have wind-driven effects on their shape similar to Jupiter's. Both have been measured using limited data from half-century-old flybys. Both serve as reference points for understanding exoplanets, the category of ice giants, or sub-Neptunes, being particularly common among discovered worlds. If their dimensions are wrong, our exoplanet catalogues are even more compromised than Jupiter's corrections alone would suggest. NASA and the European Space Agency have discussed missions to the ice giants. Proposals exist for dedicated orbiters that could study these planets the way Juno studies Jupiter. Budget constraints and competing priorities mean those missions are decades away at best. Until they happen, our measurements remain based on Voyager's brief encounters. The Jupiter revelation suggests we should treat those measurements with appropriate uncertainty. They're the best we have. Best available doesn't mean accurate. The corrections for Jupiter offer a template. Expect the planets to be somewhat smaller than textbooks claim, with shapes more influenced by atmospheric dynamics than simple rotation models predict. We won't know for sure until we send orbiters. The lesson from Jupiter is clear. Flying past a planet once or twice gives you snapshots rather than comprehensive understanding, and snapshots can deceive, especially when what you're photographing never stops moving. In April 2023, the European Space Agency launched a spacecraft called JUICE. The name stands for Jupiter Icy Moons Explorer. Its mission is studying 3 of Jupiter's largest moons, Ganymede, Callisto, and Europa, searching for signs of subsurface oceans and potential habitability. JUICE carries instruments designed by the Weizmann Institute, the same team that discovered Jupiter's true size. Coincidence? Hardly. The scientists working with Juno data knew JUICE was coming. They knew it would carry more sophisticated atmospheric sensors than any previous mission. They designed those sensors specifically to build on what Juno revealed, to take the radio occultation technique and push it even further. JUICE won't arrive at Jupiter until 2031. The journey takes 8 years because the spacecraft needs multiple gravity assists from Earth and Venus to build up enough speed. Once it arrives, it will spend at least 3 years orbiting Jupiter before entering a dedicated orbit around Ganymede. During those 3 years, JUICE will perform its own radio occultation measurements, more than Juno, at different latitudes, at different times in Jupiter's weather cycle. The spacecraft carries an instrument called 3GM, Gravity and Geophysics of Jupiter and Galilean Moons, specifically designed to measure planetary gravity fields and atmospheric properties with unprecedented precision. The data will refine what Juno discovered, confirm the new measurements, extend coverage to regions Juno couldn't access, build 3-dimensional maps showing how Jupiter's size and shape vary with time as atmospheric conditions change. This is how planetary science progresses. One mission makes discoveries that raise questions. The next mission arrives equipped to answer those questions. Each builds on the previous generation's work, pushing measurement precision higher and understanding deeper. Here's what makes the timing interesting. When JUICE was designed in the early 2010s, it was being built to study a Jupiter measured by Voyager and Pioneer data. The mission plan, the instrument calibrations, the expected observations, all based on the old dimensions. JUICE is already en route, carrying instruments designed for a planet that's slightly larger than the one it will actually find. The discrepancy is small. The instruments will work fine. The mission team will need to adjust their expectations and data processing to account for Jupiter's true size. It's a reminder that space missions operate on decadal timescales. From initial design to launch can be 15 years. From launch to arrival at a distant target can be another decade. By the time a spacecraft reaches its destination, the scientific questions it was built to answer might have evolved. JUICE will still accomplish its primary mission, studying Jupiter's icy moons. It will also serve as the first spacecraft designed with knowledge of Jupiter's corrected dimensions. Its measurements will be processed using updated atmospheric models. Its gravity data will be interpreted against improved interior structure calculations. The spacecraft becomes a bridge between the old understanding and the new. Built in one era, operating in another, carrying knowledge from Juno forward to whatever comes next. In 30 years, some future mission will probably discover that JUICE missed something too. That's how this works. Always refining, never finished. Always discovering that what we thought we knew needs correction. The mistake was subtle. Nobody was negligent. Nobody cut corners. The error came from treating a dynamic system as if it were static, from assuming that what you see at the surface tells the whole story about what's beneath. Earth's atmosphere is about 60 miles thick. The troposphere, where weather happens, extends maybe 10 miles up. Above that, the stratosphere and higher layers contain very little mass. If you wanted to measure Earth's size, you could ignore the atmosphere entirely. The error would be trivial, a few miles on a planet, 8,000 miles in diameter. Jupiter doesn't work that way. The atmosphere is the planet. There's no solid surface beneath to provide an absolute reference point. The surface is wherever you decide to define it, and scientists chose the 1 bar pressure level because it seemed like a reasonable standard. The same pressure we experience on Earth's surface felt like a natural comparison. Pressure alone doesn't account for movement. Imagine trying to measure the size of a balloon filled with water while someone shakes it violently. The balloon's surface ripples and undulates. In some places, it bulges outward. In others, it contracts inward. If you take a snapshot and measure at one moment, you get one set of dimensions. Take another snapshot a second later, and the dimensions change. Jupiter's atmosphere is that balloon. The shaking never stops. Wind patterns persist for decades or centuries. The Great Red Spot has been raging since at least the 1600s. Those bands of clouds have maintained their basic structure throughout recorded history. Beneath the apparent stability, the atmosphere churns constantly. Pressure levels rise and fall. Temperature gradients shift. The 1 bar pressure level undulates by dozens of miles as winds push and pull on the atmosphere. The Voyager and Pioneer measurements captured snapshots. They sampled the pressure level at 6 locations during specific moments in time. Those measurements were accurate for what they measured, the atmospheric state at those particular places and times. The error came in, assuming those 6 points represented the planet's stable, average configuration. They didn't. They represented 6 samples of a dynamic, varying system. Juno's advantage goes beyond more measurements. It was measurements spread across time and location, multiple orbits at different seasons, different latitudes showing different wind patterns. The data set captured variation instead of assuming uniformity. When you account for that variation, when you include wind effects in your calculations, when you map how the 1 bar level changes with latitude and time, you get a different answer. A smaller average radius, a flatter polar region, a shape that reflects the reality of a planet in constant atmospheric motion. This is the fundamental challenge with measuring anything dynamic. You have to sample extensively enough to distinguish stable characteristics from temporary fluctuations. 6 points can't do that. 26 points start to reveal the pattern. The atmosphere didn't fool us maliciously. It just behaved the way atmospheres behave, dynamically, chaotically, constantly changing. We fooled ourselves by treating it as stable. The corrected measurements represent Jupiter as it actually is, a roiling ball of gas and liquid with no fixed form, recognizing that reality forces us to ask what else we're measuring wrong. What other dynamic systems are we treating as static? Here's the uncomfortable truth. Jupiter is close. It's bright. We've been studying it for centuries with increasingly sophisticated instruments. Multiple spacecraft have visited. We have an orbiter there right now continuously gathering data. If any planet in the solar system should be thoroughly understood, it's Jupiter, and we got its size wrong for 50 years. What else is wrong? Mars rovers have been exploring the surface since the 90s. We have detailed maps, sample analysis, weather data. We're planning crewed missions for the 2030s. How much of what we think we know about Mars relies on assumptions similar to the ones that misled us about Jupiter? Venus hides beneath clouds we can barely penetrate. The surface is a hellscape of heat and pressure that crushes spacecraft within hours. Our measurements come from brief visits decades ago. Could Venus be significantly different from textbook descriptions? Mercury orbits close enough to our star that detailed observation is difficult. Only 2 missions have ever studied it up close. Do we really know its composition, its core structure, its thermal properties? Beyond the solar system, exoplanet science builds on assumptions derived from planets we can actually visit. If our understanding of Jupiter was flawed, how many of those assumptions need revision? How many discovered worlds are classified incorrectly because we're comparing them to incorrect reference standards? The tools keep improving. Juno represents a massive technological leap over Voyager. The James Webb Space Telescope sees in wavelengths and with clarity impossible a decade ago. Future missions will carry instruments we haven't even invented yet. Each generation reveals details the previous generation couldn't detect, which means each generation discovers that previous generations were wrong about something. Science works this way. You make the best measurements you can with available tools. You build models based on those measurements. You test the models against observations. When better tools reveal discrepancies, you update your understanding. The process is iterative, never finished, always refining. It forces humility. The confidence with which we state astronomical facts, planet sizes, stellar distances, galaxy masses, carries an implicit asterisk. As accurately as we can currently measure, every fact is provisional, subject to revision when better data arrives. Jupiter's corrected size is a reminder of that provisionality. We published those old measurements in textbooks, taught them to students, built theories on top of them. They felt like established facts, solid ground to build on. Instead, they were approximations good enough for the time yet inadequate forever. What else are we wrong about? Probably plenty. Dark matter might be real, or might be a sign that our gravitational theories need revision. Dark energy might drive the universe's expansion, or might indicate we're misunderstanding how space itself works. The precise age of the universe depends on measurements that future telescopes might show were slightly off. We won't know what we're wrong about until we discover we're wrong about it. Jupiter just taught us that lesson again. The question goes beyond whether we're making mistakes. It's which mistakes we'll discover next, and whether we're humble enough to admit them when we do.